Hello, 8th graders. We are going to work on lesson 7 here, and lesson 7 is a nice review of using exponents with, all those exponent rules we've been working on. But first of all, I added this comic in here. This part right here I'm circling. If you remember what anything to the power of 0 is, then the comic should make sense to you. So here we go. As always here, we could come up with a reason for any of these why they don't belong, but let's use this as a review of our exponent rules. In this first one, we are dividing. We have the same base, which is 2. So I know that I can subtract the exponents. So 8 minus 5 would be 3. So this is going to be the same as 2 to the third power. The next one going down, I have a power to a power, so I know I can multiply those. So this will be the same as 4 to the negative 40th power. And going over here to my third one, here I have a fraction as my base, but that's okay. This is going to be the same as 3 to the 4th to the, I'm multiplying, so I know that I can add those exponents. So that's going to be the same as 3/4 to the third power. And this last one here, now I have two different bases, 10 and 5, and different exponents going on. So this is the only one that I cannot simplify using the exponent rules that we've done so far. I could use a calculator to simplify this, and it would end up being 32,000. So no matter which one you decided doesn't belong, that's what they would simplify to, and you can kind of use that as your review of exponents. Okay, here are the answers for these, so no matter which 6 you chose, you can check your answers. Number 2 is asking which ones did you want to skip. I'm assuming a fair number of you would want to skip these that were dealing with division, and that's because when we're subtracting exponents, sometimes it can get tricky with negatives. So let's talk through these. I'm subtracting exponents when we divide. So 5 minus 28 would be negative 23. Negative 5 minus 4 is negative 9. 5 minus a negative 8. Remember, if you are subtracting a negative, that's the same thing as adding, and so that would be an exponent of 13. And same thing on h here, negative 12 minus a negative 20. That'd be the same thing as negative 12 plus 20, which would be an exponent of positive 8. Over here, when you're multiplying, you would add those exponents, even if they're negative, right? Just add like normal. And then when we take a power to a power, we're multiplying exponents. And remember, if we're multiplying a positive times a negative, your answer is going to be negative. Okay, in our first section on number 3, you had negative exponents on all of these. Remember, the negative exponent will kick it to the denominator. And so when I rewrite this, it's a fraction. 1 over 2 to the, now it's a positive 7 power. That's going to be the same on all of these. That negative exponent creates a fraction, kicks it to the denominator, and then your exponent is negative. And in number 4, you chose 3 of them. Here's the answers to all of them, so no matter what you chose. Here, we were trying to review this idea of a 0 power. Anything to the 0 power is going to be 1. Also, what happens if you have fractions? Well, it's going to be the same thing. You just write it out, 2/3 times 2/3 times 2/3, multiply across the top, 2 times 2 times 2 is 8, multiply across the bottom, 3 times 3 times 3 is 27, and there's your answer. Going over to D, multiply across the top, multiply across the bottom, 25/16. I could simplify that to 1 and 9/16. Either one of those is fine. So take a look at those. If you have any questions, again, please don't hesitate to ask. All right, I used a calculator to start evaluating this, and if I keep going, on the left, I would have 200. On the right of the equation, I'll have 100,000. That is definitely not going to be the same. So this is false. Okay, so far we have number 1 is true. Number 2 is going to be false. If I use a calculator on this, I'll see that my left-hand side is not going to be equal to the right-hand side. How can I change them to make them true? I could make the bases the same. So if I had 15 squared times 15 to the third, that's going to be the same as 15 to the fifth because I could add the exponents. Number 3 is also false. Again, if I use a calculator, I can see that the left-hand side is not going to be equal to the right-hand side. How could I make it true? If this one was multiplication instead of addition, then it would be true, because if I have the same bases being multiplied, I can add those exponents. Number 4 is also false. Again, if I use a calculator, I can see that the left-hand side is not going to be equal to the right-hand side, so that's false. How could I make it true? Again, if we had the same base on this one, then it would be true, because if we have the same base, then we can add those exponents. And going down to number 5, this one is going to be true. I used a calculator and I did see that both sides end up being the same. One thing you notice here is that the exponents are all the same. And then you might notice that a little trick is that 3 times 5 equals 15. So if we have the same exponents, it seems that there's a pattern we can use. We will be looking more into that pattern in the next lesson. In lesson 8 here, we're going to pick up where we left off at the very last problem in lesson 7 and look at multiplying expressions with different bases. If you evaluate both of these, you can see that they both end up equaling 1,000. And again, notice how they have the same exponent on all of them, and that 5 times 2 equals 10. We're going to expand on that coming up here. Okay, here we have another table that we've been using when we find all of our exponent rules. In this first one, you can see we started out with 5 to the third times 2 to the third, which is what we just saw. And if we expand that out, 5 times 5 times 5, that's our 5 to the third, times 2 times 2 times 2, that's our 2 to the third. This is all being multiplied, and when we have everything being multiplied, we can actually switch the order of things. And so I'm going to rewrite it as 2 times 5 times 2 times 5 times 2 times 5. Notice I still have 3 2's and 3 5's being multiplied. And now I can simplify. 2 times 5 is 10, 2 times 5 is 10, 2 times 5 is 10. And so you notice it's the same as having 3 10's being multiplied, and I could write it as 10 to the third. So let's do this first one, 3 squared times 7 squared. So I'm going to rewrite it first as 3 times 3 times 7 times 7. Now I don't really need the parentheses because everything's being multiplied, but it just kind of helps separate and see what we're doing here. I could rewrite this as 3 times 7 times 3 times 7. Again, everything's being multiplied, and so we can move the order around. And now I'm going to simplify. 3 times 7 is 21. So this is the same as 21 times 21, which is what we see over here, 21 squared. Go ahead and work on filling in the rest of the table and start again when you're ready. Okay, so I've done a few of these. Let's pause and look at these a little bit. Again, expanding it out using the same pattern that we've noticed. Hopefully, at this point, you're starting to see that if we have the same exponents on everything, we can multiply our bases together. For example, 3 times 5 is 15. As long as I have the same exponent, 3, 3, and 3, my rule of multiplying my bases together, 3 times 5 equals 15, will work. Okay, 2 to the 4th times x to the 4th. Again, I expanded that out. And when I rearrange, I can write it as 2x times 2x times 2x times 2x. And that would be the same as 2x to the 4th power. I have to have parentheses here showing that I'm taking the whole thing, 2x to the 4th power. Right here, now I'm just going to use the rule that we've learned, that I can multiply a times b and simplify this as a times b in parentheses to the n power. The exponent stays the same. This last one, I do not feel like multiplying writing all of that out. I'm going to use the rule that we just learned. So I'm going to take 7 times 2, which is 14, and then times 5, which is going to be 70 to the 4th power. Lastly, on number 2, what happens if neither of the exponents nor the bases are the same? For example, could we write this with one exponent? And no, we cannot. The exponents have to be the same for the rule that we just saw to work. For other exponent rules to work, the bases would need to be the same. So if neither of those are the same, it's not going to work.